Okay, cool. Like, we have heard about a lot of some great talks about different aspects of agents, including this like safe discussion about this like safety, about personalization, like multi-turn interaction and reasoning. So now let's start for the first question about this like foundation of agents session. So yeah, as Dan has mentioned at the beginning of her talk, there are some sayings that 2025, this year, is the year of agents. But actually, last year we have also heard those words saying that 2024 is the year of agents. And basically, this kind of voice has been there since these foundation models become popular. But agent word, this word itself is not a new concept. It has been there since decades ago. So for all these panelists, if you think about one or two key capabilities that are only become possible with foundation models, but not really there yet, then what will be the coming up top of your head? So probably we can start with the remote speaker, Jacob.
So the challenges, I think the big challenge that is ahead of agentic systems right now, I think it's pretty clearly the ability to retain memory robustly and continue working for a much longer time, right? Like with models, with systems like ChatGPT, we've kind of become used to this ephemeral AI that you kind of talk to it and then it's gone, and we've been able to extend the duration these systems can productively work for a little bit, and we've been able to have them retain information for a bit longer. But I think there's still an incredible amount of progress to be made there. And I think with what we've seen, with how these models are able to learn in context and explore new ideas there, I think this will go hand in hand with extreme increases in intelligence.
I think on this question particular, the biggest research question that I can think of is what is the limit of a single agent? So what I mean by this is, in my talk, I alluded to the fact that you can compress all these capabilities now into a single model. So merely 10 years ago, if you had a Chinese to English translation and you had English to Japanese translation, they would all be different models, and the summarization would be a different model. And the QA, question and answering, would be a different model. Now it's all one model. And the question is, how much can we continue to use fine-tuning chain of thought, RL, to compress further problem-solving strategies into these models such that it can remain one model versus multi-agent? Now, there's a lot of reasons for multi-agent. So for example, once you compress things into a parameter, you can't have access to the most up-to-date information, like what's the temperature right now, or what's going to be the weather tomorrow, things like that. You wouldn't compress that into the model. So that part of it is obvious. But what about things that people are exploring right now, where we're using multiple agents in order to have parallel trains of thought? Would that remain or would that disappear? I think that's the biggest question, the biggest missing capability, if you will, that we haven't completely figured out. And in fact, one of the reasons I'm flying red-eye flight to Toronto tonight, precisely because I wanted to be at this conference to hear answers to this question. So I'm paying attention to the talks to try and understand what will be the limit of single agent and where it will be. And then that allows us to, again, predict the future about where multi-agent systems will be.
Okay, yeah, thanks. Thanks, Jacob and Ed, for the great comments. So in my talk, I talked about the challenges in safety and security. I do think that going forward for agents, that is going to be, I would say, the biggest hurdle, one of the biggest hurdles to actually deploy these agents in the real world. I think from actually many different aspects. So one, I just mentioned we want to, essentially make the single model more and more powerful and so on. But on the other hand, we actually don't really have very good understanding. The whole community, we don't really have good understanding how these models work. And we know that these models actually have many problems. They have, even from the security side, from injection, jailbreak, but they have many actually different aspects of safety and security issues for these models. And we ultimately, we don't really understand how they work and how to make harden the model against these issues. And furthermore, when we put it into this agentic setting, then actually comparing to the traditional systems, this actually becomes even harder. In traditional systems, they developed, software engineers develop to write these programs. At least there are certain goals, certain expectations of how the systems should work. But now, when we talk about agentic systems, they are so dynamic, we actually we don't even know, we can't even pre-specify how these agents actually, what they are supposed to do. The security goals and the specifications of the program behaviors actually is completely out of the window when you have such, flexible and autonomous agents and so on. So this also causes huge problems. Now, when you have these agents running, you don't really know whether the behavior is actually expected or not expected. It's very difficult to actually even try to protect these systems. So I would say, for all these things together, given that we don't have good understanding of how these models work, and they have a lot of safety, security vulnerabilities, and so on, the agentic system is so flexible, so complex. I think the security issues and safety issues will be one of the biggest challenges.
So language models know many things, but it's pretty hard to get them to do what we want. And in practice, any organization that is good at doing this will typically employ lots of people that are very good at figuring out all the details, not necessarily just to make the language model a better language model, but to get it to do things more like what we want it to do. If you work with a person and you ask a person to do something for you, typically if you want them to do it correctly, you would explain what outcome you want rather than the precise steps that they should execute. You might also give them some hints for how to do it, but the most important thing is to get across what it is that you want them to accomplish. And unfortunately, we're not very good right now at telling LLMs what we want them to accomplish. We're much better at telling them how we want them to accomplish it. Now, and that's why it requires so much work. Now, reinforcement learning, of course, does give us part of the answer. And if you're in a domain where you can set it up as a reinforcement learning problem with a good verifier and turn the crank, it's sort of no wonder that those are the domains where so much progress has been seen over the last year. But it's still a very difficult tool to apply because it requires a lot of scaffolding. So to bring this long story to an end, where I'm going with this is that I think what we actually really need to think about carefully is how to be able to train language models directly to accomplish rewards in a way that is scalable, that doesn't require a lot of scaffolding, that doesn't require setting up some manually designed verification or simulation frameworks, where you can define a task, perhaps in natural language, that acts as the goal, train it on data, and this would have to be with offline RL because otherwise you'd have to simulate it, and actually get a model that is trying to accomplish the goal you set out for it with minimal hints about how to do it in advance. So I think that's the kind of technology that we need to develop to make all this very scalable, and I think it's still an open problem.
If I may add something after Sergey's point here that I think is useful, is that when Danny Zhao and I were essentially inventing chain of thought and we were talking about it, the motivation behind it was precisely what Sergey in a way was referring to, was that most machine learning was still dealing with large amounts of data in order to teach the model how to do something. And we really wanted to get to a point where you only have to tell the model once how to do something, the how versus what part notwithstanding, and then the model would learn how to do it, right? That was the motivation behind chain of thought. And I realized recently that this should really become a test for AGI. We have a lot of debate about when AGI will arrive, and nobody knows what the definition of AGI means. And I recently came out with what I call the grandma test. The grandma test is the following. At some point in the future, you have a robot in your house, and your grandma will tell that robot, I want the dishes to be put away this way. And I only have to explain it once. And if grandma comes to you and complains, the robot doesn't do what it's supposed to do, you know we have failed AGI.
Yeah, thanks for this very fun discussion. So probably also related to this Ed's point on this chain of thought discovery. So if we think if you think about your past experience on doing this research on agentic AI and foundation models, so what can be one or two key surprising findings, either positive or negative, that you feel that probably it is not unconventional kind of a shared thought among people in this community, and you want to talk about it. Anyone wants to start? Yeah, Jacob, you want to start?
Sure. Yeah, I think it's kind of it's always a surprise, I think, for any sort of AI system we develop. But as we were working on getting reinforcement learning on chain of thought to work, it still surprised me just how many bugs we had to work through, and just how critical that was. And I'm talking software bugs. I'm talking bugs in how we thought about the problem, and in fairly basic parts of the setup. But yeah, even fairly simple things to understand. Yeah, tend to take quite a bit of this debugging in getting deep learning systems to work. Yeah, I think it's just that they are very good at hiding mistakes.
Yeah. Anyone wants to go next?
I wasn't actually super clear on what the question is.
The surprising findings.
Yeah. So in terms of surprising findings recently, or do you think in the future?
Yeah, this question is probably for your past experience.
Okay. Well, then maybe I can offer this a little bit as food for thought, which is, I think the most surprising finding over the last couple years is really that computer science originally started as a way to manage the complexity of the problem that we wanted to solve by a very simple principle called divide and conquer, right? So the idea was you have a very complex problem, like safety, for example, and then you would divide up all the different problems, like, how do you deal with people who are asking about how to make bombs, and then kids' safety and whatever. And you would divide all these problems into its parts, then you would build modules for all of them, and then you would put it all together in a system-like way. And part of the reason why we're here in this form is because there's a set of people, a huge amount of you, I imagine, are trained as computer scientists, and the moment it's like multi-agent system, it's modularized or whatever, you get very excited because all the training that you have been, sort of receiving over decades, now all of a sudden reapply, basically, in this world, right? But I think the real surprise over the last, I would say since 2017 or so, because the transformer paper and the sequence-to-sequence learning paper I mentioned before, is that there has actually been a great convergence, right? The convergence of functionality or capabilities into a single model. And as I mentioned, because we don't know the limit of what that looks like, the big surprise is that we keep getting surprised by the compositionality of the model. And that is an incredibly powerful concept, and it's creating such big revolutions in our field because even computer science education has now got to all of a sudden change, right? How much, I have professors coming up to me asking, how much of traditional computer science should we even teach? Should we only teach them AI? Are we now a department of large models? Or is it really computer science, right? So I think the big surprise that I hope, if somebody in the audience, I don't know if there's audience questions, but if someone asks me why I keep saying 6 years, but if 6 years from now we're sitting here together, I hope we have figured out that question. Because I think, if I'm not mistaken, many of you feel a great sense of anxiety. And the reason why you feel a great sense of anxiety is because anxiety arises from uncertainty about the future. If you don't know the future, you will feel anxious. And I feel the same anxiety because I don't know how far this is going to go. And so compositionality and how far it goes is by far the biggest surprise I think we need to address as a field.
Yeah, thanks. Any more comments here?
Yeah, so I don't know if this is necessarily like all that surprising to those of you that work on these things, but I think that there is actually something pretty interesting in how language models can simultaneously be really good at combinatorial generalization, also really bad at it. In that, like, I think it's really remarkable that you could fine-tune a model to become better at some set of tasks, and that will also make it better at other tasks that are kind of structurally related. That's really cool. That's kind of the sort of thing you might expect from a person. If they practice some things, they also get better at other related things. But then it's also very easy to get into these situations where, like, you just realize just how bad the analogy that, oh, this is like a person really is. Like, you can change a prompt a little bit and get a great solution to a problem that otherwise you'd have gotten a terrible solution to. And I think it's very important to remember that a language model fundamentally works very, very differently from a person. That you know, maybe it's more accurate to think about it as a very large group of people, and when you provide a prompt, you kind of index into recalling a generation from something from the training set. But what that implies is that maybe we shouldn't think of agent training processes like the RL stuff necessarily as teaching the model something new so much as convincing it to do the thing that we want. And taking that perspective, I think, might be kind of healthy in thinking about the right space of methods in the future.
Yes, so I would say that I think the entire journey has been full of surprises. I think, so, right, so my group actually started working in deep learning, you know, very early, actually earlier than most people in the field. And also actually with Xingyun, like we started working, we were among the others to work on using deep learning for program synthesis, code generation, and so on. Even back then, like I was telling Xingyun and others, like every day, like you can call it pleasantly surprised. Like we did, like for the task that we didn't think that actually just training these neural networks could solve, it could solve it. And then the next day, the next week and next month, we give it a little bit harder task, and then we were pleasantly surprised again. It could actually, right, just by tuning, they can solve it. And then at one point, I was thinking, really, how far can we go? For sure, we are missing some critical ingredients to actually help us to get to AGI. So this is like, you know, way before ChatGPT and GPT-3, GPT-4 came out and so on. But I think one surprise is that I continue to be pleasantly surprised. Maybe at some point I should stop being surprised just how this how this path has given us like so much win. That these models can really be trained and learned to do all these crazy, amazing things. But of course, on the other hand, they also really make very stupid mistakes, and also they can be easily attacked. So that's why I think this journey has been full of surprises, and I think continuing going forward, yes, hopefully we'll be pleasant surprise, but also hopefully some of these issues can be addressed as well.
Yeah, great. So let's first probably have a final question. So yeah, it's related to this like scaling paradigm. In the past, we have seen these like different ways of data scaling, like compute scaling with like scaling up model size and also reinforcement learning. So what do we think that scaling is just the way to go? And if not, or if yes, so what's the next scaling paradigm we should envision?
I think we're running short on time, so I'll keep my answer brief. But I think a lot of the discussions around scaling that really kind of happened over the last 5 years or so, and particularly in 2023 inside of Google, almost all the conversations were about scaling pre-trained models. And I think it really missed the point for quite a while because we were already in 2023, the Lambda team was mostly working only on scaling and figuring out post-training. And even then, at this point, I feel like people are missing the point. I think there's another scaling that's happening that no one is paying attention to. And that is every generation since pretty much 2021, 22 or so, the medium-sized models become just as powerful as the previous version of the large models. So every generation moving forward, the medium model is getting benefits from training the large models, and we essentially distilling that into the medium-sized models. That very much suggests that there's another scaling law that's happening at a smaller size level. And perhaps as another answer to the surprise question would be, how far can we go with that? Will we get to a point where a medium or small size model that eventually that would run on your phone would be only 2, 3, or 4 generations behind the largest models, but still much, much more powerful than the current large models that we're already putting into production right now. If that's the case, by the way, edge inference will become more important, and your investment portfolio should change.
Yeah, more thoughts from the speakers?
I think that well, I really appreciate Ed's answer, and I also think that what scalable means in the future will probably be a bit different. My take on this is that I think one of the most important things that should be made more scalable is, as I said before, defining what task you want the model to do in a way that it actually listens to you. And I think that that's a different kind of scale. It's not about scaling so that you can use more data. It's about scaling so that you can add more tasks and more capabilities in a way that is efficient with respect to the human labor that goes into it. And I think this is a place for new methodology to make big improvements.
I think we are, taking this current scaling paradigm largely actually because we don't know how to have better, more data efficient algorithms and approaches. So I think going forward, I really view the next frontier is how we can actually develop more data efficient algorithms and approaches. So that is actually the right way to scale.
Jacob?
I think we have a very long way to go on scaling this thing we call test time compute. I think even the name test time compute is kind of, it implies a fairly low scale. Really what we're after is scaling learning in context, right? Because that's what we see these reasoning models doing, exploring new ideas and finding new insights. And, right now, the sort of compute that we spend on that, even for this, IMO contests, I think it's nowhere near where it can be if you compare it to what we spend on training systems in general.
Yeah, great. We have run out of time. So yeah, thanks a lot for all the panelists. We have a fun discussion. Yeah.
Thank you.